So in that world where you've got a number to predict or a class to predict, and also, while I didn't show it, you want to just make clusters, those things are really fully automatable. Unfortunately, the real sophisticated fun end of machine learning isn't fully automatable. And for those, by far the winner has become the neural network approaches. And the neural networks are a way of describing a model that has a lot of richness, but also some of the elements of the model are architectures that are designed through deep human thinking for specific tasks. So this is the lexicon of the language of neural networks. Most of these things represent trainable layers that we can assemble to build a neural network. And some of them are very generic, like an element-wise layer or a fully connected layer. Some of them are quite specialized, like convolutional layers tend to be very good for image recognition. I'm not going to go into how you design these things. I'm going to skip over that completely, and we'll use some that have been pre-built and show you how to use those and modify them. So we saw this one earlier. This is the LeNet model for image character recognition. It's got a kind of compact image in our notebook, but actually behind the scenes, it's got 11 different layers. And these things are a convolutional layer is kind of image feature extraction. Some of these things are purely structural. Some things like linear layer are about combining features. Softmax layer is a probability layer. And so these things have been built by somebody to be a very simple image recognition network. Let's get some data to apply it to. So these were the characters that we had before. And we can simply apply that to one of the images to get a prediction. This is let's copy this out. This is an image that's come out of the data set. And when I say apply that network to that image, we get back now a prediction. It's not a picture anymore, it's now an actual number. So I could add something to it, for example. So in terms of using them, we try to make that easy by giving them names that you can fetch using this netmodel command. And if you go to our neural net repository on the web, you'll find that there's all kinds of neural nets for different purposes, doing things like image segmentation or image content recognition or speech recognition, all of these kinds of tasks as ready to download networks. So you simply have to say, fetch the thing by name and then apply it to the data. So from a use point of view, we try to make that completely seamlessly easy. Let's not talk about oh yes, let's talk about this. So if we want to retrain for the same task, then that's really a one-step process in most cases. So let's take some new data, which is the blur of the old data, and apply it now. And actually, it still seems to have done a reasonably good job with a little bit of blurring, but you can see that now it's not doing quite so well. That blurred 4 is looking more like a 9 to it, and the 6 is looking like a 0. But if I want to train it with blurry data now, in a similar way to the way that we had classify, we have Retrain, which is basically doing the job of classify and predict, but it takes as its first argument the network that we're trying to train, and the second argument is the data that we are training it with. So here I'm just doing a data preparation to label the data, and it retrains that network. This is a lot slower. So you can see without a GPU, it's taking a good few seconds here. And this is the error between the examples it's looking at and its prediction. And as it tweaks its weights and learns from it and makes the model better, that error gradually falls. And at some point, it'll reach some level that it decides to terminate, or I can click the stop button and end it early. Oh, it's made some breakthrough discovery. And now it seems not to be doing any better, probably because I don't have enough data for it to learn any better from. And it will get to the end. And now if you apply it to that, it's now done a good job, partly because I've cheated here and used the same data. So I didn't do the test training split that I should have done. Now, by default, Retrain starts with all of the training parameters of the net as downloaded. So they've adjusted, but they haven't been completely reset. So it still does a good job on the original data. it hasn't kind of forgotten everything. But over time, by this approach, it will gradually forget what it was trained on, unless you mix your training data with the training data that it was originally trained on, so it preserves both knowledge together. Now, we can modify these networks as well. So if you are dealing with a task that is similar to something for a neural network, but not the same, then these things are all adjustable, because there's a symbolic object that is computable just like any piece of data in the Wolfram language. So by way of an example, let's get a much bigger model out. This is the one that's used by our image identifier command, but here I'm getting the actual neural network, and you can see here there's a bit more to this one. It's got 20 odd outer layers, but actually some of these layers are graph layers within them. So if I click on this one, you'll see that this one layer itself is in fact, got 23 layers within it. So there's actually about 200 or 300 layers in this network, more than I'm going to want to figure out how to code by hand. But that doesn't mean that I can't transform the thing. So one thing I could do, for example, is just take the first 10 layers of that. So I can just throw away the bottom end of the network, and now it's only the first 10 layers. And now I can see what's going on inside at that point by applying that to the image. I'm going to have a bunch of matrices. To understand the matrices, I'm going to turn them into images. And what we're doing is now getting a glimpse inside the brain at level 10 of the network. And we're seeing some of the features that it's detected. So whatever this bit of the thing that it's looking for, it found no features that matched. You can imagine some of these things might be picking out the stripes of the tiger. I don't see any that look very like diagonal stripes, but maybe if we were looking closer to the beginning of the network at level 3, then some of the more raw features would be identifiable to things that we're really looking for in the real world. What that also allows you to do is to do transformations on this, so I can replace parts of this layer, this model, with different outputs. And let's just do this live. I think I'm going to do this. So the basic idea is you do net replace part of our network, and we give a list of the layers we want to change. So I'm going to change, let's get the whole network back here so I can see what I'm doing. I'm going to change this this last linear layer to be size 3, so I can have it not predict from 4,315 things like tigers and cats and dogs, but I wanted to do rock, paper, scissors, for example. I would replace the linear layer there with a fully connected 3 layer, and I would have to do something else here with the encoding decoding. The encoding is okay because those are images, but the decoder, I want to give a new output classification language for this, which is net decoder class. And I'm going to tell it what those classes are, and I'll just call them rock, paper, scissors. Red is telling me I've got my syntax wrong because I've got one too few curly brackets going on. If I've done that right, and another bracket at the end, nope, doing something wrong here. Curly bracket missing. What I should end up with is now a new neural net that ends in a vector 3 with my new classification of rock, paper, scissors. You can see everything's black here apart from the linear layer. So those have remembered everything they know about tigers and cats and dogs. The linear is brand new, so it needs training, which is why it's red. And then I would do a net train of that against pictures of my fist doing rock, paper, scissors symbols, and it would learn how to recognize that. So this kind of transformation allows you to take those things from the world of our repository, find things that are close to the task, tweak them to a task without having to understand all the details of why there's a net graph layer in the middle. With a few basic bits of understanding about the kind of last output layers that softmax is the probability layer, linear layer, aggregates all the features together to make a final decision from, and then make that change. So let's spend 10 minutes on one key problem that you have to worry about when you're building machine learning, which is concepts of overfitting or underfitting. Because what we're not trying to do with our model is to build a model that remembers what it's seen. There's faster ways to look up data and say, is this example one we already know, than to build a neural network. We want it to generalize so that when it sees something new, it can take the things that it's learned from the features and the relationships between the features and make some useful prediction from that. So underfitting, you fail to capture enough essence from the problem, and it just makes bad predictions. That if you imagine trying to fit a straight line uh, um, to very complex data like this, in fact, that's I guess what this first example is doing, is if we only give a straight line fit to this curved data, then it can't capture the complexity of that data. A straight line is just not got enough richness to it, and that will underfit and make pretty poor predictions in places like here and here. It might happen to get lucky in some places, but on the whole, it does a poor job. Our generalization is going to look somewhat similar to the underlying model that generated our data, but it's not going to take into account, there's always going to be errors because there's noise and randomness in the real world. But if we give too much freedom, we end up with overfitting, where we get a model that is so rich that it can capture all of the data points, or nearly all of the data points. But you can see in some places it's doing a much worse model to fit to than our good model here. So this is actually a terrible model for the opposite reasons than this is a terrible model, because it's overfitting. It's trying to remember the data rather than capture the essence. And what it's therefore trying to do is effectively model the randomness that it can never capture because it's random. It's, well, philosophically speaking, it's driven by features that we don't have on the input set. And it can't capture those, so it ends up being kind of just a random fluctuations in the model that mean nothing, and those get exaggerated as you overfit. So let's talk a little briefly about a few ways to approach that. And I'm going to make a toy example here. I'm going to make some data that's roughly an exponential curve, but I'm throwing in some random noise into it. And there's not very many data points. And here is our data. And I'm going to make my own neural network. I'm just going to code this one up from scratch. It's going to be a linear 50 layer, a nonlinear layer that's got a tanh activation function. So that's what gives it the ability to do something complex, is mixing linear and nonlinear. And another one, and another one, and then we're going to have one output, the input scalar, the output scalar. So it's going to take a number, give a number, but it's got over 100 degrees of freedom in here. That these linear layer 50 are turning this into a vector of 50, and this is going to be a 50 by 50 matrix. There's all kinds of controls that it can adjust, and we're going to train that, and off it's going to go. And hopefully, if my random numbers have been useful here, and also for consistency, I've deliberately fixed a training method called RMS prop, because its default one actually is a bit too good at preventing overfitting. So I've deliberately picked a slightly weaker but efficient training method. And now let's see what its prediction does. Now, you could say this is a great model because when we take our underlying data, it's all very close to the curve that our neural net has generated for predictions. And maybe if this low feature here right in the center was a real thing, the fact that the curve dips downwards here would be capturing that knowledge. But actually, in this case, we know that the underlying model here is, well, let's look at what the underlying model is here. That before I added random noise to it, it was this exponential curve with it going from -3 to 3. That's the truth that we sampled data from and threw random noise in. So this feature in the middle is entirely imagined because it's given too much weight to the noise. The fact that somewhere here, there's the data point, was surprisingly low. It's assumed that that's a feature and it's captured it. So this is an example where it's overfitting. We're not getting the underlying essence that I happen to know is there. It's come up with a model that's capturing all of that noise. And while this might look good this time, if I generate another set of data and compare, you'll probably see that it does a very poor job. So there's three basic methods I'm going to introduce here to deal with this. One is called regularization. There's different versions of it, but I'm going to use something here called L2 regularization. I'm doing exactly the same thing as I did before, the same network as before, the same data, the same underlying method, but I'm adding this regularization parameter, and I'm training for the same length of time, and we'll see the result. And while it's thinking, I'll explain what regularization does. Inside that network are these various matrices that are trying to tweak their parameters in order to make the best prediction. So here we've got a much kind of more generalized prediction that's trying to ignore some of those outlying bits of noise. Now, what regularization does is ordinarily it decides whether it's a good or bad model by figuring out the difference between the training example points and the curve. And it adds all of that up, and that's in machine learning world, it's called a loss function. They can get a bit complicated when you're trying to do really rich things, but in this case, it's simply the sum of the errors. Now, in our overfitting example, it tried to minimize those by tweaking this line to try and go near every single point, so the sum of the errors got small. But what regularization does is it adds a bit of complexity to that loss function to say, not only is it going to punish the errors, it's also going to punish the complexity of the model. So the more the parameters in the model are not zero, the more it will say that's a bad model. In the same way that it will say it's a bad model if it's not fitting to the data. So it's taking both things into account. So basically, it's trying to fit to the data while at the same time use the simplest model that achieves the best fit, because it's going to favor models that have very small or zero parameters. There's different kinds of regularization depending on whether we're trying to minimize the sum of the squares of the parameters or just the non-zero parameters and so on. But basically, it's going to punish complex models over simple ones at the same time as punishing errors. And that compromise ends up giving us something that fits to the data, but also is not unnecessary using all of the controls that were available to it. Now, a completely different method is to dilute the data, and this is a slightly counterintuitive one. We're going to make the fit better by making the training data worse. So what we do is we do a little bit of transformation on our network by inserting a new layer, and we're inserting something called a dropout layer. And a dropout layer is a layer whose job is that whenever it's being used in training, it randomly disappears. So it's a way of killing certain parameters within the model randomly. So, imagine you're trying to learn the best ways to drive across the country. You might end up with a very convoluted route to get from one place to another that is technically shorter than everything else. But what dropout layer does is to say, okay, we're going to randomly close certain roads sometimes. So if you sometimes drove a long way up a single lane track, then find that it's closed, then that suddenly becomes a very terrible decision for that particular example, because on that occasion it was an unreliable bit of the route. So by making parts of the model unreliable, it stops it over fixating. So if we go back to our analogy about cats and dogs, if one of our features that we were learning on was the length of the ears, well, let's say the length of the tail, and say long tail represents a cat, you want it to sometimes be told, sorry, I'm not telling you the length of the tail, even though it was known in this training example. You have to do without that, because otherwise you might find its entire model is long tail equals cat, short tail equals dog, forget everything else. And if you make sure that sometimes it can't rely on tail length, then it would have to also take into account ears and fur and face shape and other things. So this dropout layer prevents model fixation. You see the training is much noisier now because every time it's updating itself, that random dropout is changing things. So what was a good model on the previous step suddenly becomes a worse one or a better one randomly. But on the whole, over time, it ends up with a model that is now richer than the previous one, but you can see it's still trying to avoid overly fixating on things like outlying data points. So we've still got some level of generalization, but achieved via a completely different method. The third one is an interesting extension on the test training set, which is, as well as having our test data and our training data, that we need to decide whether the thing worked. We're giving a third data set, which is effectively a test data set for the trainer. So we make some more validation data. And this time we tell it to train the net on the same main data, the same method, the same parameters. But periodically, it's going to take a peek at this extra training set and say, how am I doing against unseen data? So obviously, if it looks at this too much, it ends up becoming part of the training data, and it'll end up just being a bigger training set, and it'll fall into the same overfitting. But this idea that it validates it more periodically and doesn't use it for updating the parameters, only uses it for evaluating the model, means that we end up with, you can see here, two things going on. This is the best parameters being found, but this is the performance on the validation set in blue. So even though, and I'll run that again because it's a bit slow to see, even though the model can be fit better to the training data, the fact that it's not improving the the validation means that the best model it had was actually much earlier in the training process than the one it ended up with. So it goes on trying to see if it can improve a model in a way that improves the validation, but in the end it falls back to the simpler model it ended up with earlier. That was the last one where the kind of test, the validation set performance and the training performance were at all similar, so that it knew it was generalizing rather than simply overfitting. And again, we end up with another model, but one which has got some level of generalization. Now, these aren't distinct processes. We can do all three at once. Some of them are quite parameterizable. So the regularization level, we turn that down. We make a more sensitive model. We turn it up. It becomes a much smoother, blunter model. Dropout layers we can set to be minor or major. And there's also parameters you can set with, obviously we can change the validation sets to be large or small. So there's lots of things you can tweak with, as well as controls over how the training performs. But in the end, a lot of that comes down to trial and error and then validating, and you're trying to tweak the parameters of training to achieve the very best model that generalizes in the way that you need to in the real world.